So as we discussed, there are two main features of CNN, which are convolutional layer and the pooling layer. So let's discuss both of them, and let's get started by convolutional layer. So let's assume that here we have an input image, right? You might be saying that, hey, it's an array of numbers, not an image. But if you are following this course, you might have an idea that an image is always translated into an array of numbers inside Python or any other programming language. So let's say these array of numbers are denoting or representing an image, and we want to convolute, or we want to perform convolution on this whole image that we have. And here we have the kernel, right? This is also called kernel. Another name is filter, right? So we have a kernel or a filter that we're going to use in order to convolute this layer, right? Okay, first thing first. Here we have an input, here we have the filter or kernel, and then here we have the output. You might be noticing that the size of input and output are not matching. Input has 5 into 5 size, which means we have 5 rows and 5 columns, whereas output is expected to be 3 into 3. Why? And remember, our kernel is also 3 into 3. So the size of output is dependent upon input and filter sizes. So usually the output size is computed by, let's say, input size. Let me mention it over here. So let's say input size minus kernel plus 1. Why? How do we convolute over an image? So first of all, we will convolute over this part of an image, right? Okay, so we will select this sub-image. Why? Because our filter is 3 into 3, so we'll start with 3 into 3. So how do we calculate it? So first of all, we'll multiply first element with first element, and here we already have a result for the second element, which means that we have result for this window, right? So here, if you look at the calculations, we are multiplying 2 with 1, as you can see over here, then adding 0 multiplied by 0, then adding 1 multiplied by minus 1, which means 1 multiplied by minus 1, and then we are saying 1 multiplied by 1, which means 1 multiplied by 1. So it is simple. We are taking a dot product of two matrices, right? So whatever the result is, as you can see the calculations over here, the result is 3. So we are putting 3 over here, right? Now, if I remove everything from here, and I would ask you to fill the value over here. How would you fill the value over here? Obviously, you will go back. You will shift the filter over here at this window, and you will compute the dot product of kernel and this submatrix. Once it is done, you will put the value over here. Then you will shift the window over here. This process is called convolution. You're convoluting the window, right? Then once this product is also done with the kernel, you will put the value over here. Obviously, it is 3. We have already done that. Then you will move to the last value, which is going to be this, right? That is going to be this filter. Okay, I should have used a different color. Let's use this one, maybe. Okay, so maybe you will go with this filter. You will go with this window of the input image. Dot product it with kernel, and the value can be filled over here, right? Now, if you see, we have an image that has 5 columns as an input, but as an output, we are left with only 3 columns. So 3 into 3, which means that if input is 5 into 5, kernel is 3 into 3, our output is going to be 5 minus 3 plus 1 is equals to 3. So input size minus kernel size plus 1, right? There can be a question that what if we want the output size of the image exactly equals to the input size of the image. It is possible. For that, you will have to add the padding around the image. How to add the padding? We will talk about it in a minute. Right now, we're going to go with very simple concepts, and this is how it works. Now, I'm going to leave it up to you guys. Please pause the video over here and fill up these remaining values by using the dot product. So convolute over the whole input image and try to get all the values that we need over here. By the way, after first row is done, then we will move to this row. So next window will be this one, right? Once it is done, then we'll move to this one, right? Remember, window size will be exactly equal to the kernel size. Maybe sometimes if we have a 2x2 kernel, or maybe 4x4 kernel, then the window size will be adjusted accordingly. So I'm gonna close the I'm gonna end the video over here. In next video, I'll give you the solution. What are going to be the values over here? All right, so I hope you guys are able to solve this problem. You guys are able to write the missing values over here. If not, here is the solution. You can match this output with your solution. You simply had to take the dot product of kernel with the convoluted window of input image or input array. Now, I would highly appreciate if you can pause the video over here and you can write a Python code by using, let's say, NumPy to write the code for convolutional layer. Let's say input would be the input to a function would be input image and a kernel, and you should output the convoluted image. Let's see if you can do it or not. Pause the video over here and try to do it. Okay, so I hope you guys have tried it. If not, I have done it for you guys. So if I come over here, since you're working in Google Colab, so okay, let's come to that thing in a minute. So here I have already written a function for you guys for convolution. So it is receiving an image and a kernel, right? Here we're fetching the kernel height, and kernel width by calling the shape method. Since kernel and image are NumPy objects, so we can call the shape method. It will return height and width in the form of tuple. Same, we are getting the height and width of image as well. And then we are calculating the height and width of output image. Guess how? Input image height minus kernel height plus 1. The same formula that we learned over here. Yeah, over here, right? So we are computing the output image height and output image width. Once it is computed, we are creating an array of zeros, a NumPy array of zeros, and then we are writing a loop for convolution. Since you can see it is a nested loop, since we have a 2D array of kernel and a 2D array of input, so we have to slide over the input array, right? So that is why we have to use the nested loop over here. Outer loop is taking care of the height, or you can say the rows. Inner loop is taking care of the width, or you can say columns. And here we are simply calculating the dot product, taking its sum and writing the value in output array, right? First of all, we are getting the patch. Patch means the window from input image. That should be equal to the size of window of kernel, right? And then we are writing it into the output array that we created over here according to the calculated output height and output width. And we are writing the sum of product of patch and kernel. And then we are returning this output. So if I run this, so this is the convolution function for us. And then here, what I am doing is, I'm simply, let me show you guys. So let's say here I'm creating an array, a random array of random numbers. So this is a 5x5 array, right? You can create an array of random numbers as well, no worries. So this is a 5x5 array, right? And then I'm creating a kernel as well, randomly creating a kernel. And then I am applying this convolution by using the same convolved 2D. I'm calling this convolved 2D function, passing this image that I created by using random numbers. And then I'm also passing the kernel, and I'll get the image over here. Once I get the image, I'm simply outputting the image before convolution and image after convolution, right? So if you allow me to run it, and here we go. So if you see, initially we have this kind of an image, right? Randomly created numbers, and after convolution, you see this image looks like this. Well, this might not be very interesting example for you guys. So what we can do is we can try it on an actual real image. So I'm going to read an image. In order to read an image in Google Colab, I'll have to attach my Google Drive with Google Colab. For that, I'll have to run this cell. So if I click on this folder, you see here my Google Colab is not attached. My Google Drive is not attached with my Google Colab. So I'll run this cell and it will ask me for the permission to connect to Google Drive. So I'll give it my permission to connect to my personal Google Drive, continue, and I'll allow this, right? So here you will see it will reflect my drive in a second. Come on. Here we go. You see, this drive is reflected over here. If not, please refresh it, and then you might be able to see this drive over here. So if I'll click over here and my drive, this is my actual Google Drive, right? So click on dataset where I have an image. Here I have an image. I'll right click over here. I'll copy the path, right? So I'll copy this path from here, and then I don't need this, close this, and I'll paste that copied path over here. So let me comment this line because I'm going to use this code now. So I have pasted the path over here, which is my image path. Then I am image.open. I'm using image.open over here, passing the image path and converting it to grayscale just for the sake of simplicity. And then I'm creating a NumPy array of that image, and rest of the story is exactly same. Now this image is my NumPy array, just like this NumPy array, right? Using the kernel over there, and let's see how it looks like now. And actually this image is an image of handwritten digit 7. So this is the handwritten digit 7 original image, and this is the convolved image. So a filter of 3x3 was created, and it convolved over the whole original image one by one, and this is our actual output. I hope the concept of convolution is clear to you guys. If not, let me show you a few cool animations. Here we go. So right now, just focus on this first part where padding is 0 and stride is 1. What is padding? What is stride? I will talk about it in next video, right? So here you see we have this green colored filter, which is the kernel, and this blue colored input image. So filter, I mean the values of the output image. This green colored image is the output image, right? And this blue colored image is the input image. And this projection that you're seeing is our kernel. So kernel is projecting over this image one by one, you see, and it is giving us the output, right? From this animation, you can see that the projection is 3x3. The kernel is 3x3. The input image is 4x4, right? So you can calculate the size of output. 4 minus 3 plus 1 is going to be 2, right? That is why our output image is 2x2. Now, what is padding? What is stride? Give me just one more video to explain this to you guys. But before that, let me show you a very cool thing. I went to this website called septosa.io, and they've created a very cool animation of the image kernel. So for example, here, if we have, you see at left-hand side, yeah, it is left-hand. Yeah, it's my left-hand. So at my left-hand side, we have an array of image, and at my right-hand side, we have an array of again, we have an actual image that is convolved image, right? So if I move over there at any pixel of the image, you can see the actual value from that image, right? And then if I scroll down, okay, so we have multiple filters. If I want to sharpen up the image, I can use this kernel. And if I want to blur the image, I can use this filter. If I want to perform top sober, I can use this filter, and so on and so forth, right? So now here at left-hand side, we have the input image, and let me use a sharpen filter over here. And this red colored window is my kernel. So I'm sliding this kernel over the image, and at right-hand side, you can see what is the output of that kernel, right? So here you see I'm sliding it over, and you can also see the outputs as well. So here are the values of my kernel, just at bottom of each cell, and inside the cell, these are the calculated values of the kernel, right? So if I hover over any point, you can see the calculated values of, and here you can see the ultimate value that is being written at the convolved image out. So here we have the input image, and here we have the output image. If I scroll over here, you can upload your own images as well. So this is an image of an MRI scan of the brain. So by the way, it is a spoiler. This is going to be a final project for CNN. So I have uploaded the image of this MRI brain scan, and I have run this sharpen filter over it, and this is how it looks like right now, right? So you can choose multiple other filters as well. Here we go. So now it is blurred. Now the question is, which filter should we use? Well, we don't have to choose it. Neural network will adjust the values of these filters for us. So don't worry about that. Just go with a random filter, and rest of the things should be up to a neural network, right? So this is the code that we have written by using NumPy. You might be thinking that we are here to learn PyTorch. So where is the code of convolution by using PyTorch? My answer is, wait for the next video. Okay, so far we have performed the convolution by using Python, but we did it by using NumPy, right? So we wrote the vanilla code for it. And let's see what is the PyTorch equivalent code to replace this whole hairy kind of a function. So we'll simply scroll down over here. Again, I already wrote the code over here. I'll explain it line by line. Don't worry about it. So here we are simply importing the libraries that you are already aware of. Then we are writing a function called load image, right? So first of all, obviously we'll have to load the image, right? Let's ignore this function for a minute. We will come to this function when we will use this function. So first of all, we are using the image path. How to get the image path? You know that you'll have to mount the Google Drive with Google Colab. If you don't know how to do that, you have to watch the previous video. Then we are loading the image over here. So we're saying load image path. What is load image? Here we have a function for it. So we are passing the image path over here, and image size as well. We are resizing the image over here. So if the image size is not being passed, then by default, it is going to be 128 by 128, which means we are going to have 128 rows and 128 columns. And then we are saying image.open, and we are simply reading the image, converting it to grayscale. We are resizing it, right? I have commented this line. You can uncomment it according to your need if you want. And then we are converting it to NumPy. Why? Because we have to create a tensor of it, and we can only create a tensor by using NumPy array. So we are saying that torch.tensor, passing image into it, passing data type to it, which is float32. And then we are adding two more dimensions by saying unsqueeze 0. What do we mean by that? Ignore it for now. I'll come to this in a minute, right? Not ignore it, but just put it on shelf for a minute. And we are returning this image. So in short, we are loading the image, performing a bit of pre-processing, converting it to tensors, adding a few dimensions, and returning it, right? So here we have the image. Cool. Then what we are doing is we are saying input image equals to, hey, we have already done this, right? Let me comment this line as well, right? Cool. Since we have already done this part in loading the image over here, so we don't have to do it again. So let me comment this. Let me remove this line. Okay, cool. Now, here is the main magic that is happening. Remember the whole function that we wrote for convolution? That is being done over here, almost over here. So first of all, we are creating a convolutional, you can say we are creating the window for convolution, right? So we are saying that convolutional layer equals to NN, which we are importing over here, torch as torch.nn, which is neural network. And then we are saying convolution 2D, let me zoom in a little bit. And we are passing a few parameters. These parameters are really important, and I will explain these parameters later in this video. So we are passing input channel, which is going to be 1, right? Output channel here in this case is also going to be 1. What are these inputs? We'll see. Kernel size, we know that what is the kernel size? The filter size, right? That is 3 by 3. Then stride and padding. I'll also explain this thing in a minute. Then we are creating the filter or the kernel. So we are again writing the values over there on filter or kernel. We are converting these values into the torch tensor, and the data type is going to be float32. And then here is the convolutional output. So convolutional layer that we created over here, we are passing the input image that we loaded by using the load function. So input image is being passed to the convolutional layer, and we will get the output in convolutional layer, right? Or sorry, conv output. So here we are displaying both of the images, input image and convoluted image, right? So if I run it, we'll see both of the outputs side by side. There we go. So here we have the actual input, right? Input image. And then here we have the convoluted image, right? And if you look over here, the size of input image is 225 into 225, since I did not reshape it. And size of the convoluted image 223 into 223. I am not going to answer the reason. I hope you know it, right? If you know how to calculate the output size of the convoluted image, I hope you know it, right? Now, what are these 1 and 1? These things are representing the batch size and output channels. So what is the batch size? I hope you remember the batch size from our previous module, from the neural network module. So here the batch size was only 1. Now this one is the output channel, right? This one is the input channel. Since this is a grayscale image, so input channel is 1. Sometimes images are colored image, right? So at that time, input channel is going to be 3. Why? Because we have RGB, red, green, blue, colors over there. Now, if I come over here and I have to explain these important things, input channel, what is the number of input channels or in our input image? If it is going to be a grayscale image, which is in our case, then it is going to be 1. If it is going to be a colored image, then it is going to be 3, right? Now, what is going to be the output channel? Now, sometimes, actually most of the times, we generate more than 1 output channels, which means that this one input image will be translated into, let's say, multiple output image. Let's say 10 output channels, which means that there will be 10 convoluted copies created of this image. So each convoluted copy, here we have created only 1. Why? Because our output channel was 1, right? So if we create multiple output copies, multiple output channels, then the convoluted image copies would be multiple. And in every copy, there will be a different result. Why? If we will be using different kernels over there. Since we'll be working with the CNN, where we will be having neural networks that will be managing our kernels, so they will be managing the kernel for each layer separately, right? Then we have the kernel size. We know that what it is. And then we have the stride and the padding. Stride is basically, usually it is 1, right? But it can be more than 1 as well. If we want to skip the pixels, right? Here, you see, it is not skipping any pixel, right? It is taking a stride of 1, which means that it is taking a jump of 1. But here, here we have a stride equals to 2. And here you see it is taking the jump of 2. It is ignoring 1 pixel and then moving to the next pixel. Why? Because stride is equals to 2. If stride is equals to 3, then it will be ignoring 2 pixels in a line and moving to the next pixels, right? That is the stride. What is padding? The padding is the main reason why the dimensions of our output image are reducing, right? We know that when we are convoluting over the image, and if the padding is 0, it ignores the boundaries, right? That is why the output convoluted image has lesser dimensions. But if we will add padding over there, then it will, you can say, artificially create the paddings, a layer at outside of the image. If padding is 1, then 1 output layer will be, or you can say outer layer will be created around the image, around the output image. Or if the padding is 2, then 2 layers will be created around the image, right? This is how the padding and stride actually works. When should we use padding? That could be a question. Sometimes, you see, around the image, at the edges, we do not have very useful information. For example, over here, you can see the edges are not giving us any information at all. So images like this do not require any padding. But if you think the edges of an image right, are very important, then you should be adding padding as well. Why? Because if you will add padding, then the edges of the input image will be taken care of. The information from edges of the image, of input image, will be included in the convoluted image, right? So I hope you guys understood how convolution actually works. We have performed convolution by using NumPy. We have performed convolution by using PyTorch as well. I would request you guys to use this code and try to run it at your end as well, both of the codes, and try to see, and try to tweak this code according to your need and see what changes are being made into this code and outputs.